overview. The objective of this talk is to give an overview of science and math that's suitable for the non-scientists and non-mathematicians. And I promise I won't give a single calculation. Okay. So I'm going to emphasize, to use a very old cliche, the forest and not the trees. All too many of the courses given here at Mercer and everywhere else in academia that I've been in at all, they focus on solving some rather detailed problems, and these are the trees. And it's left to the student to combine the pieces and understand how the different courses fit together, except in those cases where the courses form a specific sequence, like Physics 1, Physics 2. So today's goal is to outline the overall big picture, and I'm going to sketch a framework, obviously, in one relatively short talk. It's not possible to give anything really comprehensive. And I'm hoping to give that framework, and it'll give an opportunity to see how the various courses fit together. Okay, C.P. Snow, some years back, famously lamented that there were two separate cultures, which he called science and arts cultures, and with very little overlap, which he lamented, I lament also. So the purpose here is to give people who would consider themselves part of the arts community an idea of what science and also math is all about. And as I indicated, link the various courses together to some extent. There's an equally important task of the arts community giving the STEM people an appreciation, but I'm totally unqualified to give that particular course, and I'm not even going to try. I hope somebody picks up that gauntlet. Okay, let's talk about math, and the first bullet, I think, is, we'll pause a moment, self-explanatory. Math itself is not a science, but it's closely linked with the sciences, and it's essential for many scientists to do their work. Basically, there are two types of math with a lot of overlap and a lot of development moves from one type to the other. Applied math is, as its name says, it takes theorems that are well established and techniques that are well established and apply it to solve problems, often in the sciences, sometimes in the real world. And what you take in an undergraduate course, that's generally an applied math. Pure math, so-called, is developed for the sake of understanding what can be known and what can be provable, and just to expand the subject, often there's a famous problem that a particular mathematician will try to solve. And I'm going to, oh yes, there are some key lessons that I think any student should take from their courses, but they're not the sort of thing that applies on tests. Since I don't know the background of various people who may be currently or in the future listening to a recording of this talk, I'll take two examples from high school math. The first one is elementary algebra. And if you ask somebody who's taking the course, you're very likely to get an answer that the main purpose of the course was to solve some simple equations with one unknown. But much more important, you learn how to use symbols to describe quantities that you might know and quantities that you may be trying to find out. And on TV, if you hear somebody saying, do the math, typically what they mean is do a calculation in arithmetic. So I think another key thing that you take from elementary algebra is that math is more than just arithmetic. Then the next year, one goes on to elementary geometry. And there are a lot of specific theorems, notably the Pythagorean theorem comes up, geometric constructions, things like that. But a key lesson is the importance of theorems to all of math and the essential nature of making your proof correct so that nobody finds any flaws or things to complain about. So I'm going to give a single example of how pure math evolves into applied math and even goes a little beyond that. This example is drawn from high school geometry. So about 300 BC, a fellow named Euclid, who's a Greek, he formulated what nowadays would be called plane geometry, and that's the subject that gets studied in high school. He made 5 assumptions. A modern mathematician might find that there are some others that snuck in that he didn't state. In Euclid's mind, these assumptions were self-evident. And I think the word axiom actually means that, but I'm not sure. 4 of these assumptions were, pretty non-controversial, but the 5th one he needed to make in order to get anywhere, and it bothered him. It bothered many later generations of mathematicians too. So he tried to prove the 5th postulate from the other 4, and he failed. And so did many others. So this is in detail what the 5th postulate said. You take a straight line, this red one, and take another point that's not on the line. And his assumption is that there is one and only one line that's parallel to the original line. And in case you've forgotten, the definition of a parallel line is we could extend both lines as far as we want in either direction, and they will never meet or even get closer together. They'll stay the same distance apart. So many years pass, actually more than a millennium, and it was one of the big outstanding problems, a major problem, and it was not solved. Quite a number of good mathematicians in their era tried to prove Euclid's 5th, no relation to Beethoven's 5th, but no dice. Finally, in the early 1800s, a Russian mathematician named Lobachevsky reversed the question and said, can we make a geometry where there's more than one parallel line? And he found, using totally abstract reasoning, that the answer was yes. He was able to come up with a concrete, an abstract geometry in which this was true and everything was self-consistent. He had no idea of any particular surface that this applied to, but it was about 10 years after he died, a fellow named Beltrami and a couple of others showed that it described the curved surface that's illustrated over here. It's called a pseudosphere, and it has a constant curvature, although that may not be obvious from just looking at the figure. The curvature is negative in the sense that if we trace one of these lines in this direction, they curve one way. If you go this way, they go around and they're closed. That's in contrast with a sphere where there are circles in both directions. Come on. So let's see how we go from pure math to applied math. After Lobachevsky did his work, other mathematicians, notably a fellow named Riemann, generalized on his results, looked at more dimensions, looked at surfaces that had a variable curvature, looked at a surface like the sphere that had positive curvature, and more generalizations. Then, between 1907 and 1915, so we're in this 20th century now, a fellow that everybody knows named Einstein applied this new kind of geometry, Riemannian geometry it's called, to develop a new theory, which turned out to be a theory of gravity called general relativity. And he famously, in his later years, told a 7-year-old who was having trouble with math that she shouldn't worry. His problems with math were far greater. He got a lot of help from mathematicians. In particular, in the later part of developing his general relativity, a mathematician named David Hilbert. In point of fact, Hilbert wrote the final form of Einstein's equations about a week before Einstein did, but he refuses to take credit because the real work, the insights, and so on, were due to Einstein. The interesting thing is, not only is this an application of math to a fairly fundamental scientific area, but you couldn't have a navigation system on your phone or in your car without taking into account two factors from general relativity. One, the fact that the gravitational field 200 miles above the Earth is a little bit different from on the surface of the Earth, and the other is a satellite going at around 17,000 miles an hour, even though that's a tiny fraction of the speed of light, requires a correction, a relativistic correction for that. So the essence of pure math is, as I said, to expand the field of knowledge or perhaps even create a new one. We saw the example with geometry. And then the mathematician must prove via theorems that their work is valid. Just open any advanced math book, and basically there is very little text. It's just filled with theorems, lemmas, and corollaries. A lemma is really a mini theorem that the mathematician isn't particularly interested in for its own sake, but it does a lot of the work of proving his main theorem, and a corollary is an extra result that falls out after either immediately or after a relatively simple proof. I might point out that occasionally other people find that a lemma is important in its own right and it becomes known. So I did go into a little more detail than I promised there. Let's go forward, not backward. Okay, so the structure of a theorem is basically the two words if and then. So if various assumptions or postulates, then you can draw conclusions. And then the mathematician's job is to recognize something interesting that you can prove from assumptions that he wants to make and demonstrate that his proof is correct. If it turns out that a particular postulate doesn't apply to the real world, the mathematician, the pure mathematician, won't care. He'll just shrug his shoulders and say, okay, so my theorem doesn't apply here. That doesn't detract from the validity of the theorem. So, as I indicated, all we care about is that the proof is legitimate and sufficiently detailed that any other competent mathematician could follow it and verify that indeed it's correct. And those 2 points are the key difference between science and math, as we'll see now. So let's turn our attention to the subject of science. And the most important thing I guess I can point out is that there really isn't one science. It's the sciences. There are many of them. And just pick up the course catalog, either from Mercer or from a four-year college, or even more, one that includes a grad school, and you'll see how many different courses and how few of them are directly part 2 of a sequence of a specific sequence of courses. So what the sciences are trying to do is to describe how some portion of the natural world works. And I want to call a special note to no scientist worth his name or her name would claim to be describing what nature really is, that is, ultimate reality. That's too grandiose a goal. You just say, here's how things work under this range of parameters. Usually, if you push things too far, you'll find out that your particular subject no longer fits and doesn't work as a description of reality. So as in math, there are 2 types, again, with plenty of overlap, basic and applied. So most of the sciences can be divided that way, maybe all of them, but I'm not enough of an expert to be able to make such a declarative statement that it's all. An applied scientist would take a topic that's well understood, like the mechanics developed by Newton and taught in the first couple of years at just about any college, and use those principles to solve specific problems. And then if you really want to push that concept far enough, you might actually use this knowledge to build something. And at that point, what you're doing is doing engineering. So I'm not going to discuss any particular application besides my side note to the GPS nav systems. On the other hand, basic scientists, analogous to basic mathematicians, work to expand the scope of their field of knowledge or its precision, or maybe to develop a new topic out of what had been studied. And that's generally called doing research. So the sciences share a pretty common approach. The first thing is, and by the way, it doesn't have to be this way in time ordering. You do a collection of very carefully performed measurements, and these are generally called doing experiments. And then you want a set of generally accepted rules. Here I call them principles. The two words are synonymous for current purposes. And those rules either explain the measurements, or even better, they predict the results of new experiments that somebody might try. I've had some difficulty in thinking of a good word to use because different disciplines use different terms. In physics, the term that I'm using that for this purpose is called a theory. But the important thing is that those principles and the experiments, they have to agree, or you have to improve one or the other, maybe both. And the principles governing one science may be generated by another science, and that's an important observation. So I'm going to go into that a little bit more. But first, let's talk a little bit about a much bandied about term, the scientific method. It's not exactly along the path that I'm discussing. So scientists all use rather similar methods, at least according to a textbook. They do experiments, they develop their theories or other rules, and get them to agree. Let's admit that in real life, things are never that simple because scientists are in fact human beings, much as they sometimes are considered to be either godlike or the devil, depending on your point of view. And there are plenty of arguments and plenty saying, the theorists saying, oh, your experiment's got a mistake in it. And the experimentalist saying, no, there's a mistake in your theory. And they fight about it. And eventually, though, they do come to an agreement. So the textbook version of the scientific method is you start with perhaps an educated guess at some kind of an improvement to your current field of study. And these could be called hypotheses or postulates. Then you draw conclusions that, at least in principle, are testable. And these are called typically predictions, and they will often use a lot of math. And the two bullets together, you could call it the theory. Then the key thing is one tests the predictions. And if you have a mismatch, you have to do one of two things. You modify the assumptions, and you keep making modifications until you can agree with the experimental results. Or the ideal from the theorist's standpoint, of course, is to find that there's a mistake in the experiments. Uh, one or the other has to give. So now I'm going to give an example sort of analogous to what I did in math and show how chemistry comes out of physics. So elementary chemistry is the study of how and the rules governing the combination of atoms into some specific molecules. For example, the obvious one of two hydrogen atoms getting together with one oxygen atom, and that forms a water molecule, and chemistry described as H2O or HOH. Could be described a lot of ways. The underlying rule, and from here on in, I'm starting to use the word rule, involves something called valence. And it can be calculated from the behavior of the electrons in each of the atoms. Matching of valences, it's just one for illustration of a number of the basic rules governing chemistry. But the point that I want to make is that the study of how electrons behave is really the subject of atomic physics, which is, of course, the physics of atoms. And in general, all of the rules governing simple chemistry can be derived from atomic physics. Once these rules are known, you can go ahead and do your chemistry, and you don't have to refer to the underlying physics. In that sense, one can say that basic chemistry emerges from atomic physics. I want to emphasize that's describing a logical relation between the two sciences. I'm not saying in any sense that chemistry was developed as a subject in atomic physics. In fact, the rules of chemistry were pretty well established in the 19th century, whereas atomic physics, as in any sense that we can recognize it, was a result of the physical subject of quantum mechanics, which got developed, well, starting just before 1900 and pretty well got mashed into a usable form in the 1920s. So chemistry does predate physics in time, but not logically. So the concept of emergent sciences is a really important one. I don't particularly care if anybody remembers that specific term, but the concept, I think, is important. So let's give a more general definition. Consider that there are two sciences called C and P, and I chose those letters so you can think of C for chemistry and P for physics, but it doesn't have to be. So you can say that C emerges from P as long as the underlying rules of C can be derived from the subject P. And then to work in C, to do chemistry in our example, it's sufficient to know the rules. It's not generally essential to go back to the underlying science. It's certainly possible to have one science emerge from a combination of multiple sciences. There are things called interdisciplinary subjects, and just, say that there are multiple P's in the bullet above. There is a possible exception, which I'm going to mention out of order. It's the last bullet. If you need extreme precision, then what seemed to be a extremely useful approximation, which are what the emergent sciences rules really are. They're not the whole underlying subject. If you need extreme precision, you might have to go back to one of the underlying sciences. I gave an example earlier talking about math. To build a workable navigation system, the situation is such that you might think that the mechanics from dating back from Isaac Newton's time in the 1700s would be fine. But it turns out that you need such high precision that you need to use some very modern physics in order to get useful location of where you are. So in general, the idea of having an emergent science is that you can treat more complex portions of the natural world than you could if you had to keep going back to the underlying one. So you just think about doing medicine or thinking about the molecules of living cells by studying the motion of each electron in each atom in each of the hugely long molecules called DNA, RNA, and all the other molecules involved in life, and give a shudder. I certainly would shudder at that concept. So here's a sort of a flow chart. I put physics at the root, and some of the things that come out of physics, fluid mechanics, science of materials, astronomy, cosmology comes out of astronomy and also directly from physics, so I should very likely have included a line that goes there. But atomic physics, as I said, gives you basic chemistry, and from basic or inorganic chemistry, you can derive rules for organic chemistry. And I'm not sure how many other intermediate subjects are needed. I'm not an expert. Eventually, you'll get to molecular biology, which is dealing with very complex systems. And as I indicated, you'd hate to be, trying to do molecular biology by treating it as a branch of atomic physics. Now, I submit that if you look at the rules under any of the sciences, and maybe I'm exaggerating there, but I'm not certain that I am, and ask, where do these rules come from? You typically get one of two answers. A lot of them probably still say, well, we've done a lot of experiments, and this is a summary of what we found. And we don't know anything more fundamental than that. Otherwise, you're going to find that your subject emerges from a somewhat more basic one. So if we go to the root, it's no coincidence, and it's not personal prejudice, that I put physics at the root. I am a physicist by training, but I can defend that placement. It's the science that examines the most fundamental portions of the natural world and the laws governing them, at least as they are known now, or at any particular time. As we evolve or developed from the ancient Greeks and what people like Lucretius knew and moved on. We learned more and more about the natural world, and you could study. Newton was studying things of a size that you could see. Later, you started to study atoms, which are a lot smaller. And then you started to study the parts of atoms, at least if you were becoming a specialist in this field. So I could take that physics box and break it up the way I did that previous slide and have a lot of subjects within physics that are emergent from more fundamental. But I didn't want to go into that much detail. The important thing is that the underlying principles at the very basis of physics aren't derived from anything else. It's part of physics itself, is that search. So let's take a look a little bit about theory and experiment using physics as an example. The underlying principles of physics are called a theory. And I have to emphasize that the word has an extremely different meaning than it's used in everyday speech. In everyday speech, usually people say, oh, I have this theory, meaning that they've got a guess, or maybe something even vaguer. If you ever hear somebody refer to somebody else's thinking as, oh, that's just a conspiracy theory, that's really a put down. You usually mean that it's a fantasy having little to do with the real world. But in physics, a theory, it's no coincidence that it sounds very similar to the word theorem in math. The structure of a physical theory should look rather familiar. You start off with if, and then you make various assumptions or postulates. Then you draw various conclusions, except in physics, they're more likely to be called predictions. The essential difference between physics and math is at least some of your conclusions have to be testable by experiment. And for the combination of theory and experiment to be accepted, they must agree to the accuracy that you can make the measurements in the experiments. I'll go so far as to say the strongest way we can say that we actually know something is when we have this combination of a theory and experiments that match with the theory. It's perfectly possible to have a theory that has some conclusions that you just can't test. For example, a few years back, there was a lot of news made over the discovery of gravitational waves. Einstein predicted them way back in close to the 1917 era. But he never thought it would be possible to construct equipment that was precise enough to test the really tiny effects. And that's perfectly allowed and doesn't invalidate the theory and conclusion combination. Just means that if you really want to test this, you're going to have to improve your equipment. So let's conclude this section by asking, well, how close to ultimate reality are we? And not in the sense of the Hitchhiker's Guide to the Galaxy. We talked about the building of sciences, of complex systems from more basic ones. And so what if we go in the other direction? What is the real basis of physics? Normally in a popularization, you'll hear the speaker talking about four forces that control the physical world. I put the word forces in quotes because by the time we get to our most fundamental theorem, these effects are not forces as you would intuitively think. And the four of them are gravity, electromagnetism, which in the undergraduate world is usually studied as electricity and magnetism. The fact that they merge very intimately isn't emphasized. Call it a force. It's called the weak nuclear force, and it's the effect that controls radioactive decay. And then there is a much smaller, much stronger force that holds the nucleus and its parts together. An atomic nucleus has a lot of positively charged particles and an equal or greater number of neutral particles. So there should be a lot of electric repulsion, and there is something going on, and it's called the strong nuclear force that's much stronger and is capable of holding all the parts together. So I indicated at the beginning of the talk that I was going to concentrate on the forest and avoid the trees. I'd like just to point out two very large trees at the center of physics and at the center of the forest of the sciences. These two theories match all conducted experiments over a really huge range of phenomena, from way below the size of even a proton up to the size of the observable universe. From the slow speeds of molecules chilled down to as close to absolute zero as you can get, to the Big Bang, which is supposed to be, I don't know how many millions of trillions of degrees in temperature. The names are a bit intimidating. One of them is general relativity, already mentioned. That describes, in fact, not only gravitation, but unlike Newton's gravitational theory, which required his laws of motion to talk about how suns, stars, and planets move, general relativity includes that. And then there is something called the standard model. At least most times it's referred to, it's simply called the standard model. Once in a while, you'll hear somebody refer to it in full as the standard model of particle physics, which sounds to me a little bit strange. I'll tell you why in a moment. It describes the other three forces and their interactions. And the standard model is based on several distinct applications of the very difficult subject of quantum field theory. And in quantum field theory, the ultimate object is what's called a field, and particles come out, if you will, they emerge out of the fields. So the standard model is not really a model of particles in that sense. I'm not going to go into them any further. It would be much too specific for the nature of this talk. Now, these two theories are unfortunately in conflict. Nobody has succeeded in making a quantum version of general relativity. Nobody's yet succeeded in extending the standard model into something more general that includes gravity. A lot of work has gone into this. There are people working on what they call string theory, but so far, other physicists would argue that string theory isn't even a theory because it hasn't made any predictions that can be tested. So that's ongoing work and has not yet been completed. Maybe this century somebody will. That'll be the high point of physics of the 21st century if it is. So why is this important? Why do I wish that all of the students at Mercer had seen this talk? It is the way that humanity has made consistent progress in understanding the natural world. I'm not talking about understanding of what makes great art great, what makes a great musical composition great. That's not the realm of science. And math is the single best way to create a chain of reasoning that you know you can verify that it's a valid chain, just as philosophers may do. Doing it in English, well, maybe there's a flaw hiding there, somewhere in there, and maybe not. And it's much harder to tell. So the more one understands and appreciates the kind of analyses that science can do, the better chance you have to distinguish between somebody giving you facts and somebody just spinning a line of propaganda because he wants to. He wants to convince you of something that isn't true. A very important thing is, if a reputable person, generally considered to be an expert in a field, changes his or her advice, that may very well be due to absorbing new information. It's not at all necessarily due to a mistake or general incompetence. A scientist should be willing to change conclusions given new information. And as an illustration, in the current coronavirus pandemic, the degree to which our leaders apply the methodology of science, if you've listened in to our neighboring state, New York, especially during the spring, Governor Cuomo would very frequently use the term follow the science in this question being epidemiology. It affects our chances of staying healthy. And of course, staying healthy improves your chances of surviving. So I maintain that this is a very important area to learn about and at least understand the underlying ideas. So to sum up, the general rule is first tell people what you're going to tell them, and I hope I did. Then you tell them, and you finish up by telling them what you told them. And that's what I'd like to do now. The key points. Math is basically a very precise means of reasoning. I hope you've absorbed the concept of a theorem and the if-then structure of it. And if not, just it's laid out earlier in the talk. Pure math, which has no specific application, surprisingly often find an application in science. In fact, there is a tale, and I have no idea if this ever happened, of a pure mathematician raising a toast saying, here's to pure mathematics. May it never be of any use to anyone. I would submit that if that mathematician did exist, he's been very disappointed. Now, on the other hand, science, in its general sense, is a way of understanding how nature works. And I emphasize works, not is. If you find an area where a given science no longer works, that doesn't mean that you have to abandon it in total. It just means its range of applicability is limited. It's limited to where you can predict experiments and agree with them. I think it's interesting and important to remember the concept of one science emerging from another more fundamental one. Now, in any science, this I really hope that you take, you must have a way to predict the results of an experiment. Some experiments, maybe a lot of them, maybe a few of them. These predictions have to agree within the precision that you're able to make the measurements. Otherwise, you have to make adjustments to one or the other. Improvements, of course. Finally, I discussed the idealized scientific method. And a really key point, I've heard political arguments where scientists have changed their mind as to what's important. And it's taken as an indication that they were incompetent, basically. And it's not. Much more likely, it's an indication that they have a willingness to learn from new data. And if there is one point that I would really like taken away, it's this last one. And with that, I'll ask if anybody has any questions. If you do, here's my Mercer email address. Right now, there seems to be some problem with it. Or you can contact the Learning Center. Coming to this talk, you first came to the front desk of the Learning Center and ask somebody at the desk to forward your question to me. So if there are any, I'd be happy to entertain them. If not, I'll wrap this thing up and thank you for attending. Signing off.